IEEE Standard 1100-2019 IEEE Recommended Practice for Powering and Grounding Electronic Equipment specifies the requirements for grounding security fences. Security fences shall be effectively grounded to prevent the accumulation of static charge. The fence shall be connected to the grounding system of the electrical installation at multiple points. The connection points shall be spaced no more than 25 feet apart. Each fence post should be bonded to the grounding grid. Multiple connection points are required, and you cannot jumper all fence sections to one common connection to the grid. While fence clamps can provide some level of grounding, they should not be relied upon as the sole means of grounding. Use American wire gauge number 4 or larger copper wire for grounding connections. Use exothermic welding or compression connectors to ensure low resistance connections. Inspect grounding connections regularly to ensure they are intact and free of corrosion. The grounding grid should be designed to handle both lightning and fault currents. The purpose of grounding is to provide a low impedance path for fault currents to return to the source, thereby facilitating the operation of overcurrent protective devices such as circuit breakers and fuses. This helps to minimize the risk of electrical shock and equipment damage. Effective grounding also prevents the accumulation of static charge on the fence, which can be a hazard to personnel and equipment. Static discharge can ignite flammable materials or damage sensitive electronic equipment. Multiple grounding points are necessary to ensure that the entire fence structure is effectively grounded. A single grounding point may not be sufficient to provide a low impedance path for fault currents, especially in large fence structures. The maximum spacing of 25 feet between grounding points is intended to ensure that the entire fence structure is effectively grounded. Smaller conductors may not be able to carry the fault current without overheating. Exothermic welding creates a permanent, low-resistance connection between the grounding conductor and the fence post. Compression connectors provide a reliable, low-resistance connection that can be easily installed and inspected. Regular inspections are necessary to ensure that the grounding connections are intact and free of corrosion. Corrosion can increase the resistance of the connection, which can reduce its effectiveness. The grounding grid should be designed to handle both lightning and fault currents. Lightning currents can be very large and can damage equipment if they are not properly grounded. Fault currents are the currents that flow when there is a short circuit in the electrical system. Firstly, understanding the importance of grounding begins with recognizing its fundamental role in electrical safety. Grounding establishes a reference point of 0 volts potential, which is crucial for preventing electrical shock hazards. Secondly, a well-designed grounding system provides a low impedance path for fault currents, allowing overcurrent protection devices to quickly clear faults. Thirdly, consider the specific requirements outlined in IEEE Standard 1100-2019. This standard serves as a comprehensive guide for powering and grounding electronic equipment, with specific recommendations for security fences. Fourthly, the standard mandates that security fences be effectively grounded to prevent the accumulation of static charge. Static charge buildup can pose a significant risk, particularly in environments where flammable materials are present. Fifthly, grounding the fence at multiple points is essential. The standard specifies that connection points should be spaced no more than 25 feet apart. This ensures that the entire fence structure is adequately grounded, minimizing the potential for voltage gradients and step potentials during fault conditions. Sixthly, each fence post should be bonded to the grounding grid. This means establishing a direct electrical connection between each post and the grounding system. Seventhly, avoid relying solely on fence clamps for grounding purposes. While fence clamps can provide some degree of electrical contact, they are not designed to provide the robust, low-impedance connection required for effective grounding. Eighthly, use American wire gauge number 4 or larger copper wire for grounding connections. The larger wire gauge ensures that the grounding conductor can carry the anticipated fault current without overheating or becoming damaged. Ninthly, employ exothermic welding or compression connectors to create low-resistance connections. Exothermic welding creates a permanent molecular bond between the grounding conductor and the fence post, while compression connectors provide a reliable, mechanically sound connection. Tenthly, regularly inspect grounding connections to ensure they are intact and free of corrosion. Corrosion can significantly increase the resistance of the connection, compromising its effectiveness. 11thly, design the grounding grid to handle both lightning and fault currents. Lightning strikes can introduce extremely high currents into the grounding system, so it is crucial to have a robust grid that can safely dissipate this energy. 12thly, consider the soil conditions at the site. Soil resistivity can significantly impact the effectiveness of the grounding system. If the soil is highly resistive, it may be necessary to install ground rods or other grounding electrodes to improve the overall grounding performance. 13thly, document the grounding system design and installation. This documentation should include details about the grounding conductors, connection methods, and grounding electrode locations. 14thly, train personnel on the proper procedures for inspecting and maintaining the grounding system. Regular training will help to ensure that the grounding system remains effective over time. 15thly, consider the potential for stray currents. Stray currents can cause corrosion of underground metallic structures, including grounding conductors. If stray currents are present, it may be necessary to implement mitigation measures to protect the grounding system. 16thly, use appropriate surge protection devices to protect sensitive electronic equipment from voltage surges caused by lightning or switching transients. Surge protection devices can help to prevent damage to equipment and improve overall system reliability. 17thly, ensure that all grounding connections are accessible for inspection and maintenance. Buried connections should be avoided if possible. 18thly, use corrosion-resistant materials for all grounding components. Copper or stainless steel are good choices for grounding conductors and connectors. 19thly, avoid creating ground loops. Ground loops can cause noise and interference in electronic systems. 20thly, bond all metallic enclosures and equipment to the grounding system. This helps to minimize the potential for voltage differences between different parts of the system. 21st, use a ground resistance meter to verify the effectiveness of the grounding system. A ground resistance meter measures the resistance between the grounding system and earth. 22nd, consult with a qualified electrical engineer to ensure that the grounding system is properly designed and installed. An electrical engineer can help to assess the specific needs of the facility and design a grounding system that meets those needs. 23rd, follow all applicable codes and standards. In addition to IEEE Standard 1100-2019, there may be other applicable codes and standards that must be followed. 24th, consider the impact of future expansion. The grounding system should be designed to accommodate future expansion of the facility. 25th, use a grounding electrode system that is appropriate for the site conditions. A grounding electrode system consists of one or more grounding electrodes that are used to connect the grounding system to earth. 26. Ensure that the grounding electrode system is properly installed and maintained. A properly installed and maintained grounding electrode system is essential for effective grounding. 27th, use a grounding conductor that is sized appropriately for the fault current. The grounding conductor must be able to carry the anticipated fault current without overheating or becoming damaged. 28th, ensure that the grounding conductor is properly connected to the grounding electrode system and the equipment being grounded. A proper connection is essential for effective grounding. 29th, use a grounding busbar to provide a central point for grounding connections. A grounding busbar is a metal bar that is used to connect multiple grounding conductors. 30th, ensure that the grounding busbar is properly sized and installed. A properly sized and installed grounding busbar is essential for effective grounding. 31st, use a grounding system that is easy to inspect and maintain. A grounding system that is easy to inspect and maintain will help to ensure that it remains effective over time. 32nd, document all grounding system inspections and maintenance. Documentation of grounding system inspections and maintenance will help to track the performance of the system and identify any potential problems. 33rd, train personnel on the importance of grounding and the proper procedures for inspecting and maintaining the grounding system. Training personnel on the importance of grounding and the proper procedures for inspecting and maintaining the grounding system will help to ensure that the system remains effective over time. 34th, review the grounding system design periodically to ensure that it is still adequate for the facility's needs. The grounding system design should be reviewed periodically to ensure that it is still adequate for the facility's needs. 35th, update the grounding system as needed to accommodate changes in the facility's electrical system. The grounding system should be updated as needed to accommodate changes in the facility's electrical system. 36. Consult with a qualified electrical contractor for assistance with the installation, inspection, and maintenance of the grounding system. A qualified electrical contractor can provide valuable assistance with the installation, inspection, and maintenance of the grounding system. 37th, consider the use of a transient voltage surge suppressor, or TVSS, to protect sensitive electronic equipment from voltage surges. A TVSS can help to protect sensitive electronic equipment from voltage surges caused by lightning or switching transients. 38. Ensure that the TVSS is properly installed and maintained. A properly installed and maintained TVSS is essential for effective surge protection. 39th. Use a TVSS that is rated for the specific application. A TVSS should be rated for the specific application to ensure that it can provide adequate protection. 40th. Inspect the TVSS periodically to ensure that it is still functioning properly. The TVSS should be inspected periodically to ensure that it is still functioning properly. 41st. Replace the TVSS as needed. The TVSS should be replaced as needed to ensure that it continues to provide adequate protection. 42nd. Document all TVSS inspections and maintenance. Documentation of TVSS inspections and maintenance will help to track the performance of the device and identify any potential problems. 43rd. Train personnel on the importance of surge protection and the proper procedures for inspecting and maintaining TVSSs. Training personnel on the importance of surge protection and the proper procedures for inspecting and maintaining TVSSs will help to ensure that sensitive electronic equipment is adequately protected from voltage surges. 44th. Review the surge protection system design periodically to ensure that it is still adequate for the facility's needs. The surge protection system design should be reviewed periodically to ensure that it is still adequate for the facility's needs. 45th. Update the surge protection system as needed to accommodate changes in the facility's electrical system. The surge protection system should be updated as needed to accommodate changes in the facility's electrical system. 46. Consult with a qualified electrical contractor for assistance with the installation, inspection, and maintenance of the surge protection system. A qualified electrical contractor can provide valuable assistance with the installation, inspection, and maintenance of the surge protection system. 47th. When dealing with electrical systems operating at 23,000 volts, 2300 volts, and 480 volts, meticulous adherence to safety protocols and grounding standards is paramount. The higher voltages present an increased risk of electrical hazards, necessitating a robust and well-maintained grounding system to mitigate potential dangers. The grounding system serves as a critical safety measure, providing a low impedance path for fault currents to return to the source, thereby facilitating the swift operation of overcurrent protection devices like circuit breakers and fuses. This rapid response is crucial in minimizing the duration and severity of electrical faults, reducing the risk of equipment damage, and preventing electrical shock hazards to personnel. The proper grounding of the transformer yard security fencing is particularly important due to its proximity to high-voltage equipment. The fence structure, if not adequately grounded, can become energized due to capacitive coupling or induced voltages from the nearby conductors. This can create a significant electrical shock hazard for anyone who comes into contact with the fence. Therefore, it is essential to ensure that the fence is effectively grounded to prevent the accumulation of static charge and to provide a safe path for fault currents to flow to ground. The grounding system should be designed to handle the anticipated fault currents from the various voltage levels present in the transformer yard. The higher voltage systems, such as the 23,000 volt and 2300 volt systems, will typically have higher fault current levels than the 480-volt system. Therefore, the grounding conductors and connections must be sized appropriately to handle these higher currents without overheating or becoming damaged. Furthermore, the grounding system should be designed to minimize the step and touch potentials in the vicinity of the fence. Step potential refers to the voltage difference between 2 points on the ground that are a meter apart, while touch potential refers to the voltage difference between a grounded object and a point on the ground that can be touched simultaneously. These potentials can be hazardous to personnel during fault conditions, so it is important to design the grounding system to minimize them. The use of a grounding grid, as recommended in IEEE Standard 1100-2019, is an effective way to minimize step and touch potentials. A grounding grid consists of a network of interconnected grounding conductors that are buried in the earth. The grid helps to distribute fault currents over a wider area, reducing the voltage gradients in the vicinity of the fence. In addition to the grounding grid, the use of equipotential bonding can further reduce step and touch potentials. Equipotential bonding involves connecting all metallic objects in the area to the grounding system, ensuring that they are at the same electrical potential. This eliminates the possibility of voltage differences between these objects, reducing the risk of electrical shock hazards. Regular inspections and maintenance of the grounding system are essential to ensure its continued effectiveness. Grounding connections should be checked for corrosion and tightness, and any damaged or deteriorated component should be replaced promptly. The ground resistance should also be measured periodically to verify that the grounding system is still providing a low impedance path to ground. In conclusion, the grounding of transformer yard security fencing is a critical safety measure that must be carefully considered. Adherence to IEEE Standard 1100-2019 and other applicable codes and standards is essential to ensure that the grounding system is properly designed, installed, and maintained. By following these guidelines, you can help to protect personnel from electrical shock hazards and prevent equipment damage in the transformer yard.